stretch it at all. The local gravitational attraction of Earth, of our solar system, of all the stars in our galaxy completely overwhelms the tendency of this dark energy, whatever it may be, to try to expand things.
Density is too high.
Yeah, the density is too high. There was a question here, and lots of, I would have expected from a Caltech audience. Yeah.
February Scientific American.
February Scientific American.
Pop goes the universe.
Pardon?
Pop goes the universe.
Pop goes the universe. So this current,
based on Planck's data from the new European Planck satellite.
yeah. What's the main point of the? This is the current issue of Scientific American. You're saying February. Oh, of last year. Okay, so I did not see that article. Do you remember what the gist was?
A lot of people must have missed it.
Okay.
Most
yeah.
of them don't believe that light the redshift is a property of light.
Yeah.
Light, not a description of how the universe is.
And so Scientific American proposes this? Yeah. So there are people who do not accept the redshift as being an expansion effect.
The data from the satellite.
The data from
showing the distribution.
Yeah.
And these are the people who came along and told Bell Labs.
Yeah.
I was writing on the antenna on that.
Yes. With Penzias and Wilson.
I developed the traveling wave.
Oh, fantastic. Wow. Congratulations.
And so I followed it.
Nobel Prize winning discovery, as you know.
Well, they hired two, about shortly after I left, they hired two astronomers from Caltech.
Mm-hmm.
And those people were given the challenge of finding out. And basically, they measured the 3.5 degrees instead of plus or minus a half,
Yeah.
which is what the four of us got.
Yeah.
When prior to we were getting ready for Project Echo, it was just
Yeah.
a side issue.
Yeah. Yeah.
And so, I'm trying to think of his name, the counselor, you may know prominent Bell Labs, he followed up on it, particularly since their antenna had played such a role.
Right.
Being very
Well, I'll tell you what. Let me read that article. I don't want to comment on it without having read it, but I'll.
You're seeing something that doesn't quite agree.
Yeah. Let me see what they say, but.
The number is so small.
Yeah.
If you go into the fact that it's a shift, the number is so small that it makes the universe go way out.
Yeah. Let me take a look. It is true that we now know from the microwave background measurements that the actual universe goes far beyond our observable universe. Yes, way back there.
Oh yeah, so in terms of dark matter, they're doing some studies where they think it's not as uniform. What about dark energy?
Yeah, so the dark matter, correctly, is not uniform. It's clustered where the galaxies are and where the clusters are.
Right.
We've made measurements of the dark energy, and to the degree that we've been able to make the measurements, which is nowhere near as exhaustive as the dark matter measurements, but to the degree that we've been able to do so, we've not noticed any deviation from uniformity. So it even exists in this room, but it's completely negligible, as I mentioned in my other answer there. So we'll see whether it has any tendency to clump up, but so far no such tendency has been found.
This may relate to the same thing, but from the way you described it, it sounds like you were looking for a supernova to measure distances.
Yeah.
And it seems like if the stretching were happening in a non-uniform way, then the distances might be different over there from over here.
Right.
And I'm wondering if you get a collection from
Yeah.
everywhere around the sphere, you see exactly the same.
So it's the same question.
Yeah.
It's precisely from measurements in different directions and measuring the same amount of acceleration that I was able to answer the question affirmatively as I did to you, that we claim it's uniform. Yes, right here. And then
I don't know if you're a gambler, but would you bet that would you bet that antimatter falls up and is repulsive?
So what I bet on antimatter being repulsive. So there, I think I don't have to gamble. Antimatter is just the opposite of matter, but it comes together with matter in a burst of photons, and light is a gravitationally attractive energy. Antimatter, according to all the theories, is a gravitationally attractive form of energy. It's just antimatter in that the charge of the electron would be positive instead of negative. It's a positron. but it is a positive energy density, attractive form of matter. Yeah. So there, I don't think I have to gamble. That one I think we know the answer to. Yes?
So I think I know the problem with your apple is you grabbed the Newtonian apple.
I grabbed the proverbial Newtonian. Right, see that? It was rotten at the base, at the top.
Taking into account relativity.
I figured. Yeah.
So,
okay.
Part at the beginning of this, you said there's expansion of space as opposed to things necessarily flying away.
Yeah, that's right.
So it seems like a lot of this is founded on that. How do you differentiate
Right.
between cosmological
Right.
expansion
So
and
great.
everything happening?
Great question. How do we differentiate? I said, no, it's not stuff flying through space. So it gets a bit complex, but let me give you the simplest example I know of, and it actually relates back to Caltech after Richard Tolman, who was a professor there. He proposed the following test, which has been done and verified. If you look at a galaxy's brightness, that's some number, right? But then you look at the area it subtends, it's some, angular area. The brightness per unit area is the surface brightness, okay? The brightness per unit, like the sun, it's in half a degree across, it's got some area, brightness, pretty bright thing. Okay, it turns out that in a universe where objects are zipping through space, the surface brightness is proportional to 1/1 plus the redshift quantity squared. Whereas if you go through the relativity, and the whole universe is indeed, as I mentioned, one of the great applications of Einstein's general theory of relativity, in an expanding universe, there's 2 extra factors of 1 plus z. So the surface brightness is proportional to 1/1 plus z quantity to the 4th power. So it's a much more rapid function of redshift than in the case of bullets zipping through a pre-existing space. You can measure the surface brightnesses of galaxies as a function of redshift. It's not as easy as that because galaxies evolve. The star formation rate of our Milky Way galaxy 7 billion years ago was a lot higher than it is now. Our galaxy is gradually running down, as are most other galaxies, because they're running out of fuel with which to make new stars. So you have to put in various corrections, and that's why this is not trivial to do. But the corrections are different for different types of galaxies, so you have different independent sort of data sets. And they all seem to converge on an answer that the index, I think the best measured index most recently is 3.7 plus or minus 0.4 or something like that. And so that's consistent with 4, right? 1/1 plus z to the 4th power. So the surface brightness test, the Tolman surface brightness test argues for it. You could take a more theoretical perspective and say that the only way to make sense out of general relativity applied to the whole universe is in this particular way. It actually doesn't make sense to have objects flying through a pre-existing space if you're applying general relativity to cosmology. But you might say, well, that's kind of theoretical. Are there observational things? And I would cite the Tolman test. There was one right there, and then over there.
Are there any theories that say that dark energy is a result of forces outside the universe?
Yeah, great question. So dark energy is the result of forces outside the universe. This is admittedly a minority of models right now, but they are being taken seriously by some physicists. You may have heard of, and I even alluded to, bubble universes, right? I mean, it was Einstein blowing universes out of his pipe. One idea is that there's lots of them in some bigger pre-existing hyperspace. And in some models, the universes, the bubbles outside ours, can pull outward on ours, okay? And indeed, in string theory, gravitons, the carriers of gravity, are these closed loops, unlike other particles which are tied down to the XYZ dimensions in which we live. Gravitons actually can float out into these other dimensions, the dimensions of the bulk. And in that way, then, other universes might be able to pull on ours. Now, I'm not a card-carrying theorist. I don't know why that's not in vogue right now. It's definitely not something that's talked a lot about at meetings, but I have heard it raised every once in a while, so it still is under consideration. I have one there, yes? Yeah. Oh, one back, yeah.
When this relates to the previous question before this, which is, as you say, the universe is expanding. Is it expanding on all time scale, on all the length scales?
Yeah, is it expanding on all length scale? That's something that I left out. In fact, well, I won't show it because it will take more time than it's worth, but You know,
Like, are we expanding?
right, so I have a picture of Santa Claus, a big huge Santa Claus, and I say, are we expanding? And you might be after a big lunch, but that's your fault, not the universe's fault. So we're held together by electromagnetic forces so strongly that it completely overwhelms any tendency of empty space to expand. Earth isn't expanding because it's held together by gravity, so much so that it overcomes any tendency, all right, for the expansion. Our solar system, our galaxy, even our local group of galaxies, which is a cluster of galaxies. So now we're out to about a 1 million light year scale, all right? That's why I said that when you get out to 10 or so million light years, that's where the attractiveness of gravity, given the distribution of matter, becomes sufficiently weak that the tendency for expansion takes over. Okay, so no, we are not expanding. Yes.
Does time also expand?
So does time expand? So my colleague Rich Muller at Berkeley has this book. It's called Now, and he has this idea. Again, I'm not a card-carrying theorist, and moreover, even in their research paper, they don't go into the details of what they actually mean. It's I'm not a card-carrying theorist, but the theorists I've talked to are not going woohoo about this paper. This is the next great breakthrough. They're taking a much more reserved approach to that paper. But their postulate is that with the expansion of space, time is created. And what now is just the last in this sequence of things that you would call now. And to Muller's credit, he does propose a test. He says that with this merging of the black holes that Thorne and Ron Drever, who passed away unfortunately a year before, so he couldn't get the Nobel Prize. Anyway, Ray Weiss, Barry Barish, Thorne, all their colleagues, they found these colliding black holes, and the merging of a black hole quite suddenly produces a large amount of additional space in that system. And so Muller proposes that if they look with higher signal-to-noise ratios, when advanced LIGO gets even better, at the signals that they find from these merging black holes, there will be a slight delay when the signals are actually seen compared to when they should have been seen, and that delay, he claims, will have been because of a creation of an extra amount of space, and hence a tiny extra amount of time. So to his credit, he's proposed a test, and we shall see. You know, we shall see what happens. Way back there. This is great.
Do you have any opinion on Paul Steinhardt's, you know, he became pretty controversial.
Yeah, Paul Steinhardt, yeah. So Steinhardt is one of the originators of the inflationary theory for the cosmos that postulates that in a very short amount of time, the universe exponentially expanded from something extremely small and uniform to something became extremely large, and that's why the universe is reasonably uniform, blah, blah, blah. Alan Guth at MIT and Andre Linde at Stanford were the original proponents, along with Alexei Starobinsky in the former Soviet Union. But Steinhardt and his student, now professor at Davis, Andreas Albrecht, proposed a very important modification to Guth's idea that actually rescued Guth's idea. Guth himself said there's a big flaw that he pointed out in the last paragraph of his paper, but he said, I'm going to publish this anyway. Maybe someone out there will find a way around that flaw. Steinhardt brilliantly found a way around that flaw, and thus was a central figure contributing to early inflation models. And yet in the past decade or so, he's turned completely against inflation, and is even claiming that the people doing it are not even doing science. And I understand to some degree what he's saying. Inflation has so much flexibility right now that even Guth admitted that, you know, any particular test might not be fatal to inflation because you could fix it up. And most scientists, in particular physicists, don't like that attitude. You propose a hypothesis and its tests, and if it fails the tests, you'd abandon the hypothesis. But don't be so hasty. Uranus was not where it was predicted to be. That led to the discovery of Neptune. It did not lead to the abandonment of Newton's laws of motion. People could have said, oh, Uranus isn't where it should have been, so let's abandon Newton's laws of motion. No, they said, you know, maybe there's something else hassling Uranus, influencing it, and that led to the discovery of Neptune. So don't be so hasty, I would say, to have such a strict definition of science that what you think of a hypothesis that's not testable or is too malleable for your own taste, don't go tossing that out right away. I'm a bit perplexed by how vehemently Steinhardt has come out recently, including a Scientific American letter that he and a bunch of people signed against inflationary models.
Well, it was a cyclic theory of universe.
Yeah.
That paper that he wrote, it was pretty interesting.
So his cyclic theory, basically he says there's a bunch of membranes out there, and they collide and heat up, and that's what the Big Bang was. But he has no origin, no plausible origin for all these parallel brains that collide. If anything, you might think brains might have been produced in that configuration by an earlier era of what? Inflation, right? So Steinhardt postulates the existence of these brains, but that's sort of invoking a tooth fairy just because you don't like the other tooth fairy being inflation. So, you know, it gets into personal preferences and scientific styles. I will grant this to Paul. He's not so wedded to his original ideas to then just keep on pounding on them for the rest of his existence. He went off on a completely new direction, and that is a mark of a very creative scientist, quite. So I tip my hat to him there, as I tip my hat to Muller for proposing a test. But most physicists have not looked upon Muller's recent hypothesis very warmly. Similarly, most cosmologists do not look upon Steinhardt's hypothesis in a very embracing attitude. So without, you know, getting too much into it, in part because I can't, because I'm not a theorist, that's my perception of the world right now, you know, so,
Alex,
yeah.
thank you very much.
Okay, I'll hang around.